Good morning. This is going to be the last lecture of this section on physical metallurgy, polymer deformation, heat treatment, and surface finishing. So the word surface finishing, I reworded it in the title of today's lecture as surface modification. So what happens is we spend a lot of time over the past 6 hours, really going from the basics of physical metallurgy. We talked about dislocation, we talked about crystallites, and then we really moved forward into how we actually make parts by deformation processing. We have the recrystallization. We talked about polymer molding and all sorts of aspects, making ropes, nylon ropes. And what I've been switching gear on after that was talking more about the environmental effect, the corrosion, and that got a little bit more involved, but I think it's good. I think it's good for you guys to understand corrosion. It's not taught a lot nowadays. And so today we will be covering a number of topics together. We will wrap up the corrosion aspect of this module completely. We'll talk more about galvanizing because it's so commonly used that I think it's good for you guys to understand a few basic concepts there. And that leads into surface modifications. And I'll be very brief on surface modifications. It's going to be more of a discussion, and it's the same for heat treatment. I want you guys to keep it in mind. You probably are aware that we do heat treatment on aluminum and steels, but I want to cover it very briefly. And it's going to lead way to the last 3 lectures for this fall. For those who do a 12-hour, there's going to be 3 lectures that are going to be specifically on welding and additive manufacturing. They are from last fall, but they will follow very well with what we're doing today. Okay. There was a question after class last time about these examples of plastics or PEX tubing that had an aluminum foil. And sometimes it is because I skip a step. So the reason for the aluminum foil, just so we're clear, on the first place, the reason they engineered it in there is to stop the diffusion or transfer of oxygen from the ambient air into the piping system. What happens if you have a heating system, you have a boiler, it's made out of steel or cast iron, and it's assumed by design that the water circulating in it doesn't have oxygen. Otherwise, you destroy that burner quickly. So when they made the switch to start using plastics, they had a problem of essentially corroding too quickly a lot of the key component of the heating system, and that is where the idea of having aluminum as part of the wall for the plastic was making a big difference. I believe everything else we talked about the series of steps to degradation were clear in class, so that was just a very small additional item. And in terms of wrapping up here the topic of environmental control, the main thing I want to say is plastics are not perfect, and same with composites. We talked about gasoline tanks and some of the issues with adding ethanol to the gasoline, and there's essentially a big responsibility when you make a change, an engineering change, to look at all the possible consequences. And in this case, it was, if you recall, the presence of oxygen in the water itself, so accelerating the degradation of the PEX tubing when it was not used for a heating system, when it was used for just potable water. I mentioned about these examples of pitting corrosion on copper, and I believe I was brief, but I essentially emphasized that the issue of very localized pitting, I mean, this could look like a drilling hole, is specific to the metals that have a protective layer. So we see it on aluminum, we see it on copper, we see it on stainless steel. So those 3 alloys or metals don't corrode significantly in atmospheric condition, except when you have this sort of a battery effect where you have a deposit, in this case on the inside of the pipe, making the environment very different there, and then creating enough driving force to initiate and pursue this local corrosion. And one thing that is interesting with pitting corrosion, is you'll go with the microscope after the fact and say, oh, there is a lot of chlorides in this area, so it must be because there was a deposit of chloride here. Well, if you see through this example, there's been a lot of water flowing through the hole after the corrosion was initiated. So be able to trace back that as the initial step is, I believe, misleading. So there's just a lot more to think about on what initiated it than this final condition, where there's just been a lot of permeation of water through the pit. The example of stainless steel, if you recall, I emphasized some of the remedial actions, which were very hard if you created pit to have the metal as performant as it was initially, because you essentially have these sites that will act as, for a battery effect, that are essentially pre-built into the surface before you have any environment coming in. And then I mentioned that one way to mitigate the issues with the stainless steel is to put just a very clear coat, a lacquer, that is permeable to moisture. But the goal here with the stainless steel is not to prevent the moisture from getting to the surface, but the big ions of chlorides. Those are the ones that you don't want to get all the way to the surface. And it's aesthetic here, right? It's not like you lose the thickness of that stainless steel. It's because it really doesn't look like what you want it to look like. Okay, this is a little bit of a new example, and I decided to keep it in because of the significance for our country. The Liberty Tower was made in the 1900s, and the structure itself hasn't been changed, and there's nothing here that we can say was completely incorrectly engineered. And I'll stand here because it was done by the French. It was engineered by the French, so give a little credit to that. Essentially, if you're going to have dissimilar metals, you would like the small part to be the one that is more resistant to corrosion. So an example of a roof, and that has been done before, is you have a copper roof and you use steel nails to lay it down. It's the worst that you can do because these small fasteners that you use are going to corrode instead of the copper flashing that's the main surface. So you'll lose your nails or bolts very quickly. So in the case of the Liberty Tower, they use copper rivets, and they use this copper saddle here that you can see is essentially making the tie between the armature of the skin that was wrought iron back then, so not even steel, and the entire assembly here. So you have this clamp that is small and is nailed from one side to the other. It's connecting two structural elements, and you do want it to not corrode preferentially. Now, 100+ years later, it is a problem. It's a problem because you've corroded enough the armature area that you have more friction and you have, corrosion issues. And you can blame the original designer. He's not there anymore. We have the same with the Longfellow Bridge. I was going by yesterday, and they did a great job working on the arch structure. It's a project that's been going on. I was under that bridge 7 years ago to look at those arches and try to determine if they had enough damage that would really require replacement or if they could be refurbished. And again, it's 100 years later, so you can't really expect that there won't be an expense associated with increasing the life of that bridge. It's expensive, and there are a number of reasons. The Liberty Tower, they'll try to mitigate it because nobody wants to take it out of service for a year. You have to put something else. There's a lot of tourists coming every year to see this. And the bridge, well, we use it for the red line, so we can't really take it out of service. That would be absolutely terrible. So it gets short, it gets fixed one piece at a time. There are hours where the red line train can't go faster than a certain amount because they took some shorings off, and it's a very impressive process. When we think of all our infrastructure and we think about the mindset, the standards at the time that was originally designed and what it is today, is very, very different. And it's our job as engineers to try to bridge that gap and continue maintain these infrastructures safely. So that's really it as far as galvanic corrosion. I don't want to get into a whole lot more details. You know about galvanic series. If you have the similar metals together, you do want to be careful. At the same time, keep in mind that a pump, like a water pump, does have dissimilar metals in it. So the idea that as an engineer, we're just going to avoid it all the time, from a cost standpoint, is not realistic. Now, those same pumps that I was talking about, I've been involved with manufacturers of huge pumps for municipalities that are being called because the pump got stuck. It wasn't being used for a certain amount of time, and the bottom line is some of these components, yeah, are designed to be used. If they are stagnant, nothing moves, it could be that it just won't work anymore. So it's an interesting idea that you'll allow for a design like this, but there's a redundancy. At the same time, if the pumps are made the same way and they're both not running for months before the project starts, for example, that could be a problem because there's this big piece of cast iron there, and there's a small piece of copper, there's a bit of brass, and they're all bolted together. I will say that it's a very, very simple field if you've had enough experience with corrosion to get the right mindset. There are a number of simple books that discuss it. If you're interested, I can point you to the right direction depending on what your area of interest is. But it becomes something that's very specialized. So people, for example, I've talked in this module about transmission pipelines. They have their way of handling corrosion issues. The people that work with pumps have their own way. And so it becomes very industry specific. It's been my experience. And the goal there is typically to control. You can't really prevent some degradation over time. Even if you're thinking of a building that you want to design for 200-300 years, there's going to be some cycles of inspection and maintenance associated with it, especially if it's cathodic protection. So you put a permanent anode, we call it permanent, but after 50 years, that's essentially what's been designed for. There are a lot of other mechanisms of corrosion that I did not cover. Stress corrosion cracking is important in industrial applications. It's the reason why we have so many categories of stainless steel, for example. Some of them will be susceptible to stress corrosion cracking in certain environments, some others aren't. And then you can also think that there are industrial applications where regular steel is just way better because it doesn't have the same issues that stainless steel as far as stress corrosion cracking. And one of the drivers, if you want to just have a little bit of insight there for stress corrosion cracking, it's the same problem of the stability of that protective layer. So a lot of the stainless steel will start to crack under stress because you locally break that passive layer and it initiates essentially a pit, and then it starts from there. It's a way to keep it in mind. We're not saying that you can't have it on regular steel, but it's been more of an issue with stainless steel, for example, and other alloys. So a lot of mechanism, a lot of things that I've covered on some other modules we'll have to identify for you guys. So, okay. We're moving into galvanizing, and the reason is a lot of steel, if you go to the hardware store, is going to be galvanized. Now, this page shows you the difference between a galvanizing that you'll get at Home Depot That's electroplated, unless it specifically says hot dip galvanized. Galvanized sheet that's used to make a lot of cars, body panels. Zinc paint, which is sold for a number of applications. Metallizing, which at this point means you are spraying a metal on the surface at high temperature. And a hot dip galvanizing, which is what I want to focus on today, just because it's relatively simple and it's something that I'm hoping you can remember. Okay. We have all these processes, they all use. It really depends on your application. The case of electroplated, a lot of time is so when you don't buy a fastener that looks rusty because it was in a box in the storage area of the hardware store for a year. So that's the type of criteria that they have in mind for doing this one. So there'd be a lot of extra cost to actually make the hot dip process. There's also an issue with dimensional controls. So if you dip it in liquid zinc, you're adding significant thickness and the threads are not going to work as well. The head is not going to fit as well with the drill bit, and all these details become all the son of the problem. So it's not just cost, it's also sort of the installation aspect of the fasteners that drive making them electroplated as a default. It's relatively rare except for high strength automotive machine screws to be electroplated. So how does it work? The first step that's not shown here is to take the part, and it can be very large. It could be an entire component of a bridge. These bats are typically 80 feet long or so, and you know what you put on a truck normally is 45 feet long, so you're able to put about anything that you're going to put on a construction site, you can dip it in there. One aspect that's important here is, and you'll see there's some drill holes at the end of the plate, because if you want to galvanize the inside, you need the zinc to be able to get in and get up. You clean those surfaces before, so a lot of times it's going to be, there's going to be steel fabrication, it's stored outside, it gets a little rusty, it gets thrown in acid bath for cleaning, and then it gets galvanized. What is interesting with galvanizing is, so long as that acid cleaning is done correctly, there's not a lot of issue about the zinc falling off the surface. What becomes an issue a lot of times with galvanizing is trying to put a paint on the galvanizing. So the reason why you'll see in a lot of stores and on the highway, you'll see galvanized guardrail, for example, that you see the grains, so you know it doesn't have anything more than the zinc coating. And one reason is if you try to put paint on it, a lot of time it's going to fall off. So it looks worse than not doing anything. So there are shops that will specialize in preparing the surface of the galvanizing to put this coating on. And there are two issues you're faced with. One is degassing of the zinc itself. So a lot of times from practice, people know that if you wait a year to paint a galvanized surface, it's going to have had the time to degas, and it's going to be easier to do. The other aspect is some of the flatness from those grains make it hard for the paint to adhere. So what they do in shops making structural components that are both galvanized and painted is they'll literally buff the surface. So they essentially lightly sand the entire surface to create a roughness for the paint to stick to. I mean, they may look like very small details, but in the grand scheme of things, they are the reason why there's issues on projects. People saying, well, that's not really what I wanted, and I'm not happy. Is there any question about, because that's about it for hot dip galvanizing. Yes?
Yeah, I was just thinking about the automotive industry.
Mm-hmm.
So they do galvanizing?
Yes.
So they have to go through this process of
Very good question. So the question about what does the automotive industry do? So they use sheet metals, and that's the schematic right here. So you were ahead of me one slide. And what happens with the galvanizing is it's thrown into a liquid back, but then it's heat treated. And what the heat treatment does is two things. It does the degassing, so it gets all the extra components out of that coating, but also it creates a roughness because there's a transformation taking place, an oxidation of the surface that creates a really good roughness for the paint to adhere to. And that was really key in the automotive industry for them starting to use it. And the other aspect about the automotive industry is it's at the detriment of exactly how useful that galvanizing is, because about half of it you kind of lose in the process. Half of the protective aspect of the zinc that you put on, you lose by creating that roughness from the heat treatment. Thank you. The second issue, if I can add about sheet galvanizing for cars, is when you have an accident, it's one reason why the repair is never going to be as good as the original construction, because if they come and they do some sanding of the surface, welding, whatever happens there, typically doesn't receive a galvanizing treatment after that. So it's going to rust easily. And that is because the galvanizing is only going to protect you over a small distance. What do I mean by that? So on the screen here, I have a thin sheet of metal, a steel, and there was a self-drilling fastener thrown to it. And I'll pass those around along with the cross-section. We're going to talk about that in surface modification. So it has a drill bit on it, and it's galvanized. So very interesting piece of component, because instead of having two processes, one where you drill the hole, the second one you come back and put a screw in it, it all happens at once. So locally, you expose the surface of the steel. And in buildings, this was an expensive museum where they had to keep a moist environment inside the building, like an aquarium type situation or a special library. What happens is you're going to corrode, you're going to lose some zinc. So what we're looking at on the middle image is this is approximately where the hole is on the sheet. I put a little square there. And then you can see you don't have any of that white layer. This is the galvanizing. And you don't have any of that left near the hole. It's all gone. And then it's the original thickness after a certain distance. That distance turned out to be about 1/4 of an inch or 6 millimeters, something of that order. And if you want to think about it simply, it's kind of the size of a big droplet. So you have moisture on that surface. You can have some droplets sometimes, but you can't expect to be able to reach out to galvanizing that is beyond that area of shared electrolyte. So the electrolyte is only shared in the vicinity of the hole, so it doesn't matter that you have so much zinc further away, it's not going to protect you anymore. And that's the threat as far as this specific application, where, say, after 3 years, you've essentially exhausted the galvanizing that can protect this threaded area, and then from there on, you're going to be susceptible to the corrosion. So you have to do something. You're not going to last the original 50-year design. Yes?
Would it almost be better to be immersed in water so that it's all in a single electrolyte?
Yes. So as far as the benefit of the galvanizing, the question was, would it be better for the building to be submerged? So yes, if the building is submerged, it's going to be able to consume all that zinc because it's really shared in the electrolyte. And that's the difference between the pump that I've talked about. So a pump, if you think about protecting a pump and you put a sacrificial anode for when it's in stored position, that anode can be 10 feet away because it's all submerged. In this case here, for everything that we see that is more just, I guess, atmospheric condition is where you need the zinc to be very close to where it's going to get consumed. So typical examples of where I've been called in are, say, electrical appliances for the tunnels here in Boston, or even some of the street stuff where they think that they've got what they wanted, but it was in reality electroplated instead of galvanizing. So only 2-3 years down the road, it's starting to lose thickness because all that layer is gone. What you can expect, and this is not, this is not any guarantee here, but people think of something at galvanized as 25 to 50-year life, even if it's in the ground. So when you have piping to go on the roads for water drainage from one ditch to the other, that's what they're thinking about. So it's not permanent. The electroplated, because it's about 1/8 of the thickness, you can do the math. It's going to go away relatively quickly, especially if it is a very moist environment. If you have salts in there, one aspect that is interesting, and I want you to think about as engineers is when you put that zinc on the surface. Now all of a sudden, you're not really thinking, if you remember last class I showed some corrosion rate for steel. Well, it doesn't matter anymore because it's not really the steel that is in contact with the environment. At that point, you are looking at what is the corrosion rate of zinc in the environment. So it's a very different equations in that case. Okay, so one reason I passed the fastener around is there's a whole series of things you can do to steel to improve the surface hardness. And what that allows you to do is to make that fastener a drilling component and at the same time not be too brittle for the application. So some of the processes that are relatively inexpensive is carburizing. So you take it into the oven and you make a reducing atmosphere that essentially allows the carbon to diffuse into the components for just, let's say, half an hour. You put it in there and then you cool it off. Now on that surface you have more carbon, and I mentioned carbon increase the strength of steel, so you modified it just on the surface. Some of the other processes, nitrating, it does the same thing. You can do it by implantation if this is a very special medical application that you want to do something right there on the surface. So there's a lot of cases where you want to be able to prevent a break of the entire component, but you like the surface of it to be very hard, wear resistant, and able to also resist crack initiation. When I brought the axle in class to show the crack propagation lines, that surface was treated to have a higher surface hardness to resist wear in this case. And the intent was, okay, well, if I have a crack that does initiate in this hard layer, it's not going to break right away. So I'm going to get a big warning sign. I'm going to get a huge crack in the axle. But then you need to have a way to inspect that if that's going to be your strategy. If your strategy is to say, well, I want to be able to detect a problem before I have a failure, then you need to be able to inspect. So the example of carburizing, and that's the cross-section that I circulated, you can see it at the root of the thread. So the left image essentially is the inside. So you have the crest here and you have the root of the thread, and it's square. And you can see that it's a lot darker and a lot finer microstructure here than it is in the core of the part. This is really a cross-section. So what you find in the microstructure, and that's something we'll talk about a little bit earlier, is it's a tempered martensite on the inside But on the surface, it still is the martensite. And the reason is it's got so much carbon in it that it just stays harder. So it's in what we call in the Rockwell C range. It's very highly resistant to wear. And so that's a good application for making a drill bit that is also your permanent fastener. And there are ways where you can do that heat treatment preferentially on the tip and not have it on the thread itself. That's a very, very smart way to do it, so you don't risk the crack initiation on the threads, but then it's more expensive. You have to engineer that so the carburation or the nitration doesn't get to the structural part. Okay, so that leads well into surface modification that I wanted to discuss with you from just a general perspective. So let's say we've made some parts and now we want to use them. We can make the surface harder. And some of the advantages, again, is wear resistance, fatigue initiation, because you raise the yield strength on the surface. The shot peening is the second example here. It looks complicated, but it isn't. So essentially, you have little balls. It could be steel balls, or aluminum or stainless steel, depending on what you are shot peening. It's in an enclosure, and it gets projected on the surface. Each time you have an impact of that ball against the surface, you compress it. So it creates a layer of residual compression on the surface when all these impacts take place over the component. So in the aerospace industry, a lot of times it is considered an improvement. So it's a way to avoid having to do repairs, but it's not necessarily, I've been in situations where doesn't necessarily allow you to increase your stress level on the component. So it's to enhance the actual performance, but it's not used necessarily to change your design parameters. There are cases, I believe, with helicopter blades that is different, that they couldn't go without using the beneficial effect because there's so much fatigue loading on them that if it wasn't for surface compression, they would fatigue really quickly. But those remain components that need a regular inspection because you don't know if in some areas you had an anomaly in your feedstock, in your process conditions, or it was shaded and it didn't work the way it was supposed to. So you have to either really control very tightly the process or use it as essentially something that's reducing your maintenance. Metallizing was the example of the train axle where they came with, it's essentially a torch that you feed metal powder into it or metal wire. It gets melted and projected on the surface. It can be from a plasma or from just heat. Those two ways of doing it have advantages, disadvantages. You need to protect that environment, so there's a shielding gas involved. One aspect with metallizing in general is the necessity to prepare the surface. So if you're going to come and project metal onto another metal, a lot of times you have not only to remove the paint, but you have to create a sandblasted texture that's going to allow you to adhere the new metal into the old metal. So metallizing for wear resistance, to some extent we could think of adding zinc to steel as metallizing, although it is specifically for corrosion control. So that was the other area as far as surface modification. We do a lot of things to metals to make them more adapt to the environment. When we're thinking about the organic coating, if you recall for steel, the goal is to prevent moisture and oxygen from getting to that interface and starting the reaction. It's a very, very hard thing to do. So you need a very dense they call it a hard epoxy, to be able to resist in submerged condition, for example, to the penetration of the moisture all the way to the interface. And you need a good thickness. And preferably, you want these immersed environment not to be years, so you have a dry cycle to actually get whatever got out in terms of moisture and oxygen. So the main disadvantage is if you're thinking about putting on something that is very, very dense as an organic coating on the surface, it's a lot more at risk for peeling and spallation because it's not flexible. It's a rigid plastic. So same thing that we discussed with the metal coating, you need to blast the surface, keep it really dry, and sometimes you need an intermediate bond layer that is going to accommodate the difference just in thermal expansion, for example. So there are a lot of challenges, and that's why it doesn't work all the time. There are cases where they'll say, you know, this specific process will last 10 years, 15 years under submerged condition, but in some cases, I believe it's still not a complete continuous excursion, that there's supposed to be some cycle of a dry. Yes?
So, in organic coating, is plastic the only kind of material that is used, or any other kind of material?
Okay, so the question was about what exactly I mean by organic coatings, right? So, yeah, so you have plastics that are thermoplastic. They're not very common, so a lot of times it's a thermoset base. When we think about an epoxy, it's a thermoset base if you think about longer term. And then you have the kind of a coal tar coating that they'll put sometime that is really more of a petroleum raw material that you put some fibers in it to save some money, and it stays relatively flexible. So it does have some good longevity. Sometimes it will dissipate in the environment, so they'll put a membrane to protect it from dissipating and staying, you know, with the metal component that you're thinking of. But I mean, from my standpoint, we're talking about everything that is not metallic. And it really depends on your application. So if we think about rebar, for example, that you put in concrete, sometimes they will put a coating on it. And if it depends if the idea is to protect against the chlorides, that's easy. If it's really to protect against moisture, that's very difficult. So these are things to keep in mind. Typically, if you put together a concrete structure, it's very expensive to repair. So you hope for that not to crack even in 25, 50 years. I'd rather go back to a rusty bridge and fix it than a concrete beach that's just all in pieces and holding itself. You have to essentially rebuild at that point.
For these zinc coatings, so in terms of protection, hot dip galvanizing is the best method?
Okay, yeah, about the zinc, you asked about the best method. So the hot dip gives you the most thickness. If you're able to live with the consequence that it's hard to put an extra coating on it, if you're also willing to deal with dimensional changes that requires different types of attachment, it's a great process. It adds to cost to the structure, but it's definitely is robust to having damage during installation. That's the biggest asset with something like a zinc coating, that you will allow for scratches and small dents and not compromise the integrity of the bridge. There is a downside. I'm glad you asked, because if you're thinking about very high strength steel that has this carburizing on the surface, for example, the zinc can generate hydrogen producing environment in corrosion condition, depending on your pH, depending on your environment. In that point, it can embrittle your steel during service. So if you buy a fastener that is a grade 8 bolt, it should not be galvanized because it's beyond that threshold where it's at risk. So there's, and everything, you can't galvanize everything, and that's one example where it can be very dangerous. Thank you. The metallic coatings, we talked about galvanizing, but there's so many things, you know about chrome bumpers. So, and chrome is also used in aviation to protect against the environment. If you're going to use a metal like chrome that is more inert to the environment, then you're at risk for what happens if that seal is breached. And that's what happens with the chrome bumpers. That doesn't happen with the zinc. So it's a tough decision, and it really depends on your application. Cathodic protection, we've talked about it a couple times. We talked about it in the context of concrete, where I said you have to have a lot of anodes nearby because the electrolyte diffusion and sharing in concrete is not as good as in water. And then we talked about the atmospheric protection. That is another case where you can't hope to protect the facade of a building by throwing an anode in the ground. That's just not going to do anything. Although, in principle, you have your electrical connection and everything will be fine. The same with metallic plumbing in buildings, where, of course, you can put some interaction with the electrical system and put essentially a potential, but whether that is actually going to protect the inside of the pipe depends if there is any connectivity there as well. So you need the electrical connection being shared and the electrolyte connection to be shared for the cathodic protection. And that really is where, for buried structure, foundations for buildings and pipelines, for example. Water pipes are a very good example where it's cast down. You can just be protected. You throw a bunch of anodes along the way, and it's going to make sure that until those anodes are consumed, you're not going to have a problem. And that's where, when I say until they're consumed, you're supposed to monitor that. And that's why they have these access holes where you go and check, do I have the potential that I'm looking for? And then one limitation with this cathodic protection in the ground is the same problem where if your soil is dry, maybe your corrosion rate is not as high, but if the anode's too far and it's not sharing the electrolyte, it's useless. You may as well not have it. So those are the things that get monitored after an installation, and they're the things that also the designer of the system is looking for to see, is this a good application for putting in cathodic protection? What kind of potential I'm looking for? And where do I need to put the anodes? How close, how deep, and all those details, they all matter. Everything is in the details for something like that. And in general, that's the challenge with corrosion control, where you have an idea of the environment, but you don't necessarily know it that well. So I'm glad you guys asked questions. I think you hopefully gained something here. So very briefly about heat treatment. And that's, again, is kind of a way to bridge between what we're doing today and the last 3 lectures that are going to be on welding. This is a phase diagram, and if you take aluminum, a lot of times aluminums for airplanes is essentially heated to the point where it's in solid solution, so there's only one type of crystals in the microstructure, and it's cooled off where it wants to transform into 2 phases. Now, depending on your cooling rate and the temperature that the transformation is taking place, you're going to form large precipitates, that's the high temperature case, or very, very fine precipitate, that's the low temperature case. So there's a process here with aluminum where you have to take it from hot, and when you quench it, all you do is prevent all these transformations here of making precipitates from taking place. You just completely avoid the diffusion process, and then you heat it up again. And that's what we call the aging. So when you have a 6061 T6, it was solution treated to a single phase, quenched to freeze that microstructure. Now that quench condition is not hard. It's essentially soft. And then you go and reheat again to increase the strength by forming precipitates. So the reason you form the precipitates is thermodynamics. It's the driving force. That's what the phase diagram tells you want to do. And what they do to the inside of the aluminum is impede the movement of dislocations. So the precipitates just really, if they find enough, they are within your grains. So they're in the playground and they are obstacles. If you do that transformation at too high of a temperature, they are their own grains and they don't have that strengthening effect anymore. So it's brief here, but that's what you see on that curve of taking an aluminum alloy, heating it up. It was solutionized, quench, and then there's a stretching process. Let's just forget about that for now. Just the aging is what we're looking at on the chart. What the aging does is it goes through a peak, and then after a certain point, those precipitates get together, they grow to be bigger, and you lose your strengthening effect. Essentially, they become their own grains. It's the simple way to think of it. That makes sense? You seem not sure.
Yeah, but I think
So, we do use aluminum a lot. This is a specific application of this radio telescope that has a very specific ditch structure to look at what the other side of the world does and other things. What you see, the outside enclosure is white. That's kind of to protect against the environment. And then the inside enclosures get the system that can tilt in two directions. This is about 200 feet or 80 meters in diameter. And it needs to stay to the same shape within some tolerances when you tilt it. So this is the type of joints that you'll have in these structures where you want the entire assembly to be sufficiently light. So, because they put these a lot of times on mountains, so the foundation you can get is only as good as it can get, and all the drive system is influenced by weight. So if you say the system is going to be 5 times the weight, then you need a lot bigger bearings, bigger drive systems. So a lot of driving force for using an aluminum alloy is where I'm getting at, and making it a tubular structure, a web structure that is weight efficient, just like a crane. You know, you just got little members here and there. Now, when I worked on that project, one challenge that was so specific to that industry is they did not use the concept of a gusset plate. And they should have, really, in a lot of cases. They did sometimes, but this is an example of really like you put a bunch of tubes together and you have welds that are transverse to the tube, which are susceptible to fatigue loading. So the variation of this is a bunch of gusset plates that you assemble together, and then you get your tube, you make a slot in the tube, and you assemble it, and then weld it on each side. You don't weld the end here because that creates a weld that's in tension, and that's loaded in shear. So you avoided some of the detrimental effect of making the weld by creating more area for the load to transfer into that joint. It's just so important. And it's a requirement in the bridge building code, for example, but in other applications, people do what they want. So I mean, you could call one advantage of this, if you're thinking about making a sealed frame that doesn't have any moisture coming in, maybe that's a reason for doing this. But otherwise, generally, you want to avoid, first of all, having so many complex shapes coming together and having to be cut in different angles. So that's an example here of a crane that has the gusset plates and is essentially more able to resist cyclic loads without a failure. There was a crane collapse that we went over, and that was one of the problems. You know, they had these things welded to the corner and get transverse weld. So for aluminum alloy, very, very specific example of data points here showing you Where the metal was reheated, the aluminum was reheated but not melted, is where it becomes the softest from welding because you lose your precipitates. You reheat it up again and cool it. And that is where your strength will go down from, this example, we're talking about a yield strength of 40 KSI. So that'd be maybe 275 megapascals, something like that. And then it goes down here to 15 in that region that was heated. It becomes a regular soft aluminum because you've lost all your precipitates. So other examples where you want to avoid this is aircraft components. So if you have a de-icing system, because especially here in Boston, we travel even if it's cold, so they circulate air from the engine in the wings, but they can't heat up the wings too much. If they really become hot, they'll lose their strength because it's aluminum. So some of the primary structures in wings on small aircrafts are not aluminum because they worry if they lose some control over the heating system that it's going to be a problem. What I'll say for steel is there's just a very, very different behavior. And the way I'll describe it is you still go from, you're here on the steel. So you still start from a solid here. This is a solid in the case of steel. And what happens during the quench, instead of what I call freezing the microstructure, there's so much driving force when you water quench or oil quench steel that you'll induce a transformation. It's not going to stay like it was. And that's why when you quench steel, it becomes very high strength and very brittle. These are the kind of differences in microstructure that you get. They just look very different, right? In this case, this is the low strength case where you got big grains of pure iron that are going to drive your yield strength. So it's going to be very, very low strength. And then the other case here is it's all intermingled, and that's your high yield strength, low ductility and toughness. And there's a bunch of combination you can do. Generally, if you're going to quench steel almost all the time, you reheat it up, and that's called tempering. So it's a very, very different process. So aluminum, when you quench, no strengthening. You heat it up, you get your strengthening. The steel is the opposite, where when you quench it, it goes into this relatively brittle phase. It goes to a martensitic transformation. That's the name of it. So it becomes from a cubic structure to a tetragonal structure, very hard to deform. And the goal with reheating up is to gain back some of the ductility at the expense of a reduction of that yield strength. That's really how it works. So I hope that it was helpful. And again, there's a lot of follow-ups after this live lecture that you can do, but it's kind of making a bridge. Hopefully now you know a little bit how we take a piece of metal and make it into something useful. So thank you.